Good morning, my dear friends. I welcome to all to a new platform, Tesla Institute of Physics, where we can find easiest and finest way to learn the concept of physics with a too much fun. So let's begin from a chapter that includes black body radiation. So everyone know light is a quantum of energy packets, or we can say light is a bundle of energy packets, and when the light moves it carry energy with itself, as we study in quantum mechanics. Okay, so my question is that how can we see an object? So in order to see an object, there are two different things that can happen. First thing, the light can pass from any object or any source to directly human eye. Okay, we can see an object by two different phenomena. Okay, suppose this is human eye. Okay, and this one is a candle. Okay, so in order to see an object, we can perform two type of things, that light can directly move to the human eye such that we can see the object, or another phenomena, the light falls on any object and reflect from that object and falls on the human eye. So this is the two different way for which we can see the objects. Okay, and when we take the second case, that is light fall on an object and reflect to human eye, but there are some objects from which light never reflect. Okay, so we can say, suppose we take an object here, suppose light fall on that object, but it never reflect to eye. So in such case, it appears black in color. So black is not a color. Black is the non-reflected part of the light. Okay, when the light does not reflect or does not radiate from that object, it appears black in color. Okay, so we find some bodies in which when we incident the light, it absorbs all the wavelength of light incident on it. Okay, and if we observe the light radiation, what we find, in case of light, mainly there are three type of phenomena occurs. Three different type of phenomena occurs due to the effect of light. Suppose I here take a candle, okay, and taking an observation by taking three different objects. Okay, so for the first object, when the radiation incident or the light incident, what happens, from that object the light reflected. Okay, suppose in second case, when the light incident on that object, it is transmitted. After passing the body, the light is transmitted. But when for some objects, when the light is incident, then it absorbs all the light. So in first case, we can say that is the reflection of light. First case is reflection of radiation or reflection of light. In second case, here we can say that is the transmission of light, transmission of radiation. But in this case, there will absorption of radiation. So generally, so light gives three different characteristics, or radiation gives three different characteristics. One is reflection, another one is absorption, and another one is transmission. So when we incident a radiation on any object, we see these three different type of phenomena. Okay, but the question is that when the objects absorb all the radiations, then it turns to black in color. It seems to be black. It appears to be black because the different color of the object is because of the reflection of the wavelength. Okay, because we say the radiations that emitted from the sun contains different wavelength of light, out of which we can able to see visible light which contains 7 type of wavelength colors that varies from V to R, that coincidence say Viv gear. Okay, so that varies from V to R. Okay, so in case of visible light, there are different wavelength of radiations consists. But when we take the condition of sun, from the sun there are large number of radiation emitting, but all those radiation does not possess color. But visible light possesses some color radiation, and the color radiation of visible light is due to the change of wavelength, due to the different wavelength of the visible light. Okay, and when the wavelength changes, there will be the color effect arises. Okay, and we say, suppose when we observe a tree leaf, it seems to be a green structure, green color. Green color means we can say when the visible light fall on the leaf of the tree, it reflects only the green wavelength of light. Okay, so that's why we can observe the green color. Okay, so when a radiation propagates, we mainly observe three different phenomena, that is reflection, absorption, and transmission. Okay, but in case of absorption, it absorbs all the radiations incident on it. Okay, and the absorption of radiation is measured by a absorption coefficient, that is A lambda. Okay, absorption coefficient, that is A lambda, and this absorption coefficient measures the amount of energy incident to the amount of energy absorbed. Okay, for a body we can say the absorption spectrum may be 20%, maybe 50%, maybe 80%, and when the absorption spectrum is high, means we can say it absorbs maximum radiation incident on it. Okay, so in order to understand the black body radiation, we have to focus on this absorption spectra. Okay, absorption spectra. Okay, so for any radiation, we mainly find three different: reflection, absorption, and transmission. But when we study the black body, what we find? For a black body, radiation. Okay, so when we find a body which has the characteristics like it absorbs all the radiations incident on it. It absorbs all the radiations incident on it. That means there is no reflection. There is no reflection, there is no transmission, but only the absorption takes place in case of that body. Okay, and when the energy radiation absorbed, then we can say that is a black body. So we can say what is a black body. So a black body, or we can say body which neither reflects nor transmits but absorbs all the heat radiations incident on it, is called a black body. Okay, so generally if we take a carbon black body, carbon black body, so in case of carbon black body, the absorption spectra is around 99%. But if we say a body absorbs 100% of the radiation incident on it, when a body absorbs 100% of radiations incident on it, then it is called a perfect black body. And a perfect black body is just a theoretical concept. Okay, so in case of carbon black body, the absorption coefficient is around 99%. Okay, and let's move towards the black body radiation. Okay, so black body, in case of black body, what we find? The black body absorbs all the heat radiations incident on it. Suppose we take a body, so not only a black body, but all the different bodies can absorb the heat radiation. Okay, but there is some radiation emitted from that black body. Okay, and also other bodies emitted some radiations. Okay, suppose we consider a body is placed in a region where there is a continuous flow of energy towards that body. Okay, that means we can say, suppose we take a condition like, suppose we place a body in light. Okay, so when you place a body in sunlight, what happens? It absorbs the radiations incident on it. Okay, so now take that body and place in a region where is a temperature variation. Okay, or we can say where is a constant temperature. Okay, constant temperature region. Okay, so we place a body such that it can absorb the radiations incident on it, and we take that body and place in a constant temperature region. Okay, so first thing, when we place the body in sunlight, what happens? It absorbs the radiation such that when it absorbs the radiation, its temperature gradually increases. Its temperature gradually increases because of the absorption of radiations. Okay, so let place the body in a region where there is constant temperature. Okay, so now if we observe that body, what happens? The temperature of the body is very much high than that of the surrounding. Okay, so the temperature of the body is very much high than that of the surrounding, and when the temperature of the body is high than that of surrounding, means it emits the radiation. It emits the radiation. Okay, but if it is a general body, if it is a normal body, then it can simply emit the radiations and come to the same temperature level, and they becomes thermal equilibrium. But if we take a black body, what happens? In case of black body, we say there will be no transmission or reflection of radiations. Okay, so in order to make transmission or reflection, or in order to make the radiation, we have to make a small hole on the surface of a black body. And when we make a small hole on the surface of the black body, then what we find, there will be continuous emission of radiations from that black body with the different temperature range. Okay, so there will be continuous emission of radiations from that black body. Okay, and this continuous emission of radiations contains different colors, contains different colors. So it contains different color means what? There must be a different wavelength of radiation. Different wavelength of radiation. So when there is a different wavelength of radiation emitted from a black body, then that is called black body radiation. Okay, and a black body radiation happens when we place a black body in a constant temperature region. In a constant temperature region. Okay, so at a constant temperature region, the body emits the radiation at different wavelength range. Okay, so radiations coming out from the black body is called a black body radiation. Okay, and the black body radiation, or in order to understand the concept of black body radiation, scientist Fery, okay, scientist Fery design a black body in the laboratory. Fery Blackbody. Okay, so Feries Blackbody is a double-walled copper hollow sphere. Okay, so it is a double-walled hollow copper sphere. Okay, in which the inner surface is coated with lamp black color. Okay, so here we can design. So a Fery Blackbody is a double-walled hollow copper sphere So this is a double-walled hollow copper sphere with inner surface coated with lamp black. Okay, so why he take coating of lamp black inside the hollow sphere? Because in case of lamp black color, the absorption spectra is around 96%, and another one is platinum black. Platinum black. Okay, in case of platinum black color, the absorption spectra is 98%. Okay, so what in Feries Blackbody, in case of Feries Blackbody, the inner surface is coated with a lamp black color, because lamp black color possesses maximum absorption coefficient. Okay, and he made a fine hole on the surface of that body. Okay, such that through this hole the radiation can enter. Okay, and he made a edge-like structure just straight to the hole. Okay, that means when the heat radiations enters into that black body, it incident on the edge surface and it reflect to one of the wall. Okay, and this wall is coated with lamp black color, means it absorbs some of the radiations. Okay, and walls are made perfectly reflecting. Okay, perfectly reflecting, that means when the radiation incident on the black surface, it absorbs some of the radiation that incident. Suppose here the radiation incident has the wavelength of lambda. Okay, and when it incident on the edge surface, it reflect to one of its wall, and at this wall it absorbs some radiation. Okay, and it is reflected to another surface. Okay, and at the another surface it also absorbs some of the radiations, and again it is reflected. Okay, so as the walls are made perfectly reflecting, so as like once the radiation entered to the black body, it makes multiple reflections inside the black body, and in each reflection it absorbs the radiations. Okay, so in each reflection the body absorbs the radiation such that the maximum of radiation incident on the black body can be absorbed. Okay, so as it absorbs all the radiation, means its temperature gradually increases. It's in a high temperature range. Okay, so if we place that black body in a region where there is a below temperature from the body, okay, and when there is a below temperature from the body, what happens? There will be a radiation. There will be radiation when the surrounding temperature is below than that of the black body temperature. When the temperature is low, means it makes radiation, and when it makes radiation, these radiations coming out from the body are generally called black body radiation. Okay, and let us analyze this black body radiation. As the temperature of the body changes, important thing, as the temperature of the body changes, the color effect of the radiation also changes. As the temperature of the body changes, the color effect of the radiation also changes, means there is a variation of wavelength with the change of temperature. There is a variation of wavelength with the change of temperature. So the variation of wavelength with change of temperature is called black body spectrum. Is called a black body spectrum. So let's analyze this black body spectrum. Okay, so that is the experiment that performed by Lumar. So black body spectrum was first performed by Lumar and Pringsem, okay, in 1899. So that means there is an experimental study on black body spectrum was taken by Lumor and Pringsem in 1899. Okay, and as per Lumor and Pringsem, the black body radiation varies like, here we take a variation of wavelength along x-axis and energy along y-axis. Okay, so when Lumor and Pringsem study the black body radiations or the radiation coming out from the black body, what he find, at the different temperature range, the wavelength of the radiation also changes. Okay, and he take the temperature range like Lumor and Pringsem Lumor and Pringsem first study the black body's radiation spectrum, and as per the Lumor and Pringsem, when we take the variation of wavelength with the energy of the emitted spectrum, what we find, the variation of wavelength with the different temperature range. Okay, so let's take, this is 1000 Kelvin, this is 2000 Kelvin, this is 3000 Kelvin, and this is 4000 Kelvin at a different temperature range. So as per Lumor and Pringsem, when the temperature range increases, the wavelength peak also increases. Okay, so wavelength peak increases means we can say that it acquires maximum energy states. Okay, whereas the temperature of the black body increased, the peak value also increases, and the maximum energy states lies in case of the black body, means we can say the energy of the black body also increases with a increase in temperature. But there is one thing that have to mark here. Okay, at a maximum energy state, for a constant temperature, the maximum energy state at a constant temperature, at maximum energy state, wavelength of the radiation decreasing, the maximum wavelength, okay, means we can say the maximum energy at which will lies at a constant temperature, that wavelength continuously decreases. This is lambda 2, this is suppose lambda 3, and this is lambda 4. What does it means? The wavelength corresponding to maximum energy state at a constant temperature gradually decreases with rise of temperature. The wavelength corresponding to maximum energy state at a constant temperature gradually decreases with the rise of temperature. Okay, and the different conclusions that from the experimental curve we find are, so what are the different conclusions from the curve? First thing, if we observe the curve, these curves are continuous curve. Okay, so we can say black body spectrum is a continuous spectrum. Black body spectrum is a continuous spectrum. Okay, second things, if we observe, the wavelength corresponding to maximum energy state gradually decreases with increase of temperature. Okay, means if I take this one is T1, this one is T2, this one is T3, this one is T4, what do we find? T4 greater than T3 greater than T2 greater than T1, but the wavelengths lambda 1 less than lambda 4 less than lambda 3 less than lambda 2 less than lambda 1. Okay, so the wavelengths gradually decreases with the rise of temperature. Okay, so we can say the wavelengths corresponding to maximum energy gradually decreases with increase of temperature. Okay, so that's why lambda m, that is the wavelength at a maximum energy state. Okay, wavelength at a maximum energy state is proportional to 1 by T, reciprocal of wavelength. Okay, and lambda m equals to some constant or lambda mt equals to constant, and this concept is known as Wiens displacement law. Wiens displacement law. Okay, so the wavelength corresponding to maximum energy state is inversely proportional to the temperature, and this concept is known as Wiens displacement law. Okay, another conclusion also we may draw here, that is, if we observe the spectrum, what we find, initially the energy gradually increases with the rise of wavelength. Okay, so energy increases initially, but after a maximum energy, after reaching maximum state, it then decreases. Okay, another important thing from the curve is that if you observe the area under the curve, at low temperature, the area under the curve is small. But as we increase the temperature, the curves becomes wider. The curves become wider means its area gradually increases. And when the area increases means we can say with a rise of temperature, the energy or the area under the curve also increases. Okay, so we can say, we can make a conclusion here, energy of the Blackbody spectrum is directly proportional to fourth power of temperature. That means E proportional to fourth power of temperature. Okay, so that implies to E equals to some constant sigma T fourth. Okay, E equals to sigma T fourth, and this is called Stephen's law. Stephen's law on blackbody radiation. Okay, and Stephen's law measures the area under the blackbody radiation curve. Okay, so you can see the area under the blackbody radiation curve gradually increases with a increase of temperature. Okay, so these are the different conclusions that we draw from the blackbody radiation curve. Okay, so today's class is all about this blackbody, Feries Blackbody and blackbody radiation. Okay, so if you have any doubt, then you can make comment. Okay, so never forget to press the subscribe button, and you may press the bell icon in order to find the notifications of the upload videos. Okay, so thank you for your cooperations.